Surfing Math Lessons presents an intuitive introduction to limits. Recall that the concept of limits was mainly motivated by our need to understand real value functions of a real variable. These functions have domain and range sets contained in the numerical model of the reals. To better visualize these objects, we take two different copies of the real line and consider on each copy either the domain set or the range set, but not both. We then construct the Cartesian product of these two copies, and in this new setting, we can visualize the function throughout the use of its graph. Due to the nature of the numerical model of the reals, of particular interest is a function's behavior as its domain set clusters around one of its limit points. We covered this and many other important ideas needed to fully understand calculus in a previous video. I will put the link on the screen and in this video's description just in case you may need to look some things up. Make use of the chapter in that video's description to help guide you on what you may need. By a clustering, we mean a process in which an approximating set or a variable defined on it approximates, accumulates, or gets close to a limit point C. For us, there are three types of clusterings, either from the left of the limit point, or from the right of the limit point, or from both the left and from the right of the limit point. The main idea we will use is the following. On each clustering process, we think about the variable x as moving along points of the approximating set S towards the limit point C. I will now proceed to explore a function's behavior during a clustering process throughout three different examples. Each of these examples will provide us with useful information on the key aspects we will need in order to make an intuitive definition of the concept of limits. First example. Use the following graph to determine the behavior of the function f of x as x approaches 0. We start the problem by quickly finding the domain of the function, which in this case is the open interval -3, 2. To understand the behavior of f of x as x approaches 0, we refer to the graph of the function and look for its values as x moves in the open interval -3, 2 towards the point 0. Now recall that the symbols x arrow 0 means that the domain set of the function approaches 0 from both the left of 0 and the right of 0 respectively. To be more specific, we check the behavior twice, once per each direction. So say we want to determine the behavior of f of x as x approaches 0 from the right of 0. Then, as x moves in the open interval 0, 2 towards 0, the function ranges from values in the open interval 1, 3 towards the point y is equal to 1. To see this more clearly, we use the following visual aid. Here we track the variable x by using the green square. This in turn generates a tracking of the point x f of x in the graph of the function represented by the yellow square. By looking at the values of the y-coordinates of this yellow square, we then generate a tracking of the behavior of the function represented by the red square. As the green square moves towards 0, the other two squares move in accordance with this movement in the graph of the function. The end result is that f of x clusters around 1 as x approaches 0 from the right. Likewise, if x approaches 0 from the left, then x moves in the open interval -3, 0 and towards 0. During this process, the red square approaches the value y is equal to 1. Hence, in this case, f of x clusters around y is equal to 1 as x approaches 0 from the left. To finish up the example, we note that the behavior of f of x remains the same as x approaches 0 from the left or from the right. Thus, f of x clusters around 1 as x approaches 0. Second example. To use the following graph to determine the behavior of the function as x approaches 0. We start the example by quickly finding the domain of the function. In this case, the domain of f of x is the disjoint union of the open intervals -3, 0 and the open interval 0 to 3. We now proceed to do the analysis by using side approximations. As x approaches 0 from the left, it eventually lies in the open interval -3, 0, and we can track it by using the green square. This in turn induces two additional trackings given by the yellow and red squares. From this visual aid, it's clear that as the green square approaches 0 from the left, the red square approaches the value y is equal to 1. Hence, in this case, f of x clusters around 1 as x approaches 0 from the left. At this point, we kind of understand the purpose the squares play in the analysis. In order to be more efficient, I will continue to include the visual aid in the remaining examples and refrain myself from mentioning the squares. You can always revert to the first example to remind you what do the different squares track. Now we still need to find the behavior of f of x for the other side approximation. Note that as x approaches 0 from the right, it eventually lies in the open interval 0, 3 and moves towards 0. In this case, we see that f of x clusters around the value y is equal to -2. We conclude that as the two side approximations are different, the behavior of f of x near 0 is completely determined on the direction from which x approaches 0. Let us do one more example before formalizing an intuitive definition for limits. I want you to pay close attention on how I break down this example. Third example. Here we are asked to find the behavior of the function as x approaches -1 and as x approaches 1, respectively. Even before attempting a solution, let us verify the domain of the function. Here the domain set is the open interval from -infinity all the way up to infinity, or in other words, the entire real line. Clearly, -1 and 1 are points of interest, and this point partitions the domain of the function into three subintervals, namely the half-open, half-closed interval from minus infinity to minus 1, the open interval from minus 1 to 1, and the half-closed, half-open interval from 1 all the way up to infinity. We begin the analysis by concentrating our attention to the limit point 1. Remember that this requires we check the behavior of the function for each direction of approximation. We do this as follows. As x approaches 1 from the right, x moves in the open interval 1 to infinity and towards 1. Note that during this entire clustering process, h of x behaves as the constant function y is equal to 2. Now we do the other side approximation for the same limit point. As x moves closer and closer to 1 from the left of 1, it is eventually walking over the open interval minus 1 to 1, where h of x behaves as the constant function y is equal to 1. Hence, in this case, h of x behaves as the constant function y is equal to 1 as x approaches 1 from the left. Notice that h of x behaves differently when x approaches 1 from different directions. Now we work on the second limit point. That is, we examine the behavior of h of x as x approaches minus 1. As x approaches minus 1 from the left, we see that h of x behaves like the constant function y is equal to 3. Now, as x approaches minus 1 from the right, h of x behaves like the constant function y is equal to 1. Notice that in this case, h of x does not have a unified behavior, but rather its behavior depends on whether x approaches minus 1 from either the left or the right. We conclude that h of x does not cluster around any point or behaves as a constant function during the process of x approaching minus 1 or x approaching 1. However, we remark that h of x is the constant function y is equal to 3 as x approaches minus 1 from the left. It is the constant function y is equal to 1 as x approaches minus 1 from the right, or as x approaches 1 from the left, and it is the constant function y is equal to 2 as x approaches 1 from the right. After these examples, we are better equipped to give an informal and intuitive definition of the concept of limits. Definition of the two-sided limit. Consider the function y is equal to f of x. Let x be a variable defined on the domain of this function, and let c be a limit point of this domain. The number L is set to be the limit of f of x as x approaches c if either f of x approaches L or f of x is equal to L as x approaches c. That is to say, L is the limit of f of x as x approaches c if either the range set of f clusters at L or f of x is the constant function y is equal to L as x approaches c. By replacing x approaching c with either x approaching c from the left or x approaching c from the right, we obtain the corresponding definitions for the one-sided limits. Note that in example 3, the range of the function was a set containing exactly 3 points. In this case, the range of the function cannot cluster at any point as it's not an infinite set. However, The noted observation of example 3 tells us that the function h of x behaves like a constant function for each of the one-sided approximations. As the goal is to understand a function's behavior during a clustering of its domain set around a limit point, we include the option of f of x is equal to L in the definition to account for functions as the one in example 3. I leave this here as a technical detail. In order to be more efficient, we use the following notation. Here we specify the limit computation throughout the lim symbol, which lies above the chosen process, and then specify both the function under study and the result of the function's behavior, denoted by L. This notation is optimal. Cutting corners by not specifying the process or the corresponding function can yield confusion and errors in final answers. So it's a good idea to write the notation completely, even when working examples or practice problems, in order to develop muscle memory. I will often refer to the last two notations as side limits. Now we would like to see this new notation in action. Before we do this, we need to point out a small observation which will allow us to solve many problems in the future with ease. Observation: the side limits might be different. We saw this when working examples 2 and 3. In the case of example 2, we concluded that f of x approaches 1 as x approaches 0 from the left, and f of x approaches minus 2 as x approaches 0 from the right. Hence, in this example, neither f of x clusters around a point, nor was f of x constant as x approaches 0. By our new definition, the limit of f of x as x approaches 0 does not exist. We can generalize this example's conclusion into the following tool. The limit of f of x as x approaches c is L if and only if both side limits are equal to L. Let us demonstrate the new notation and the above tool in the following examples. Example: use the graph of the function y is equal to g of x to find the limit of g of x as x approaches minus 3.5 and as it approaches 2, respectively. Clearly, the domain of g of x is the entire real line. Now we tackle this problem one part at a time. Let us first find the limit as x clusters around 2. As x approaches 2 from the left, we see that g of x gets closer to the y-coordinate of this blue dot, which is exactly the value of g of x at x is equal to 2. Hence, g of x approaches g of 2 as x approaches 2 from the left. We can estimate that g of 2 is around 5.4 or 5.5 from the information given by the problem. Now, as x approaches 2 from the right, we see that g of x gets closer to the y-coordinate of this blue dot. Hence, in this case, we have that g of x approaches g of 2 as x approaches 2 from the right. As both side limits at the limit point c is equal to 2 agreed, with the value L is equal to g of 2, we conclude that the limit of g of x as x approaches 2 is L is equal to g of 2, which is roughly 5.5. Now we answer the second question. Again, we break the analysis by computing side limits. First, as x approaches minus 3.5 from the left, the function g of x is getting closer to a value which is between minus 6 and minus 8. Roughly speaking, minus 6.7. Second, as x approaches minus 3.5 from the right, g of x is tending to a value which lies between 1 and 2. Roughly speaking, 1.5. Now you may be wondering about this blue dot corresponding to the point minus 3.5, g of minus 3.5, line in the graph of the function. Doesn't it play a role in our answer? Well, no, it doesn't. This is the key distinction which makes limits different from simply evaluating the function at the limit point. Limits care about the tendency of the function as x clusters around a limit point, and not of the actual value of the function at the limit point. To finish up the example, we see that the side limits are not equal. The left side limit being roughly minus 6.7 and the right side limit being roughly 1.5. By our previous tool, we conclude that the limit of g of x as x approaches minus 3.5 does not exist. Before we finish this discussion, I want to do a last example which will uncover we have been using a hiding assumption all this time. Last example, use the graph of g of x to find the limit as x approaches minus 2 and as x approaches 2, respectively. The first thing we observe is that the domain of g of x is the disjoint union of three open intervals, namely the open interval from minus infinity to minus 2, the open interval from minus 2 to 2, and the open interval from 2 to infinity. That is to say, the points x is equal to minus 2 and x is equal to 2 must be excluded from the domain. However, these points are limit points of the domain of g of x and thus play a role with respect to the graph of g of x in this case. Just as in the previous examples, we work one problem at a time and break its analysis by using side limits. As x approaches 2 from the right of 2, x is walking over the open interval 2 to infinity and getting closer to 2. By looking at the graph of g of x, we observe that the closer x gets to 2 from the right of 2, the function g of x becomes increasingly smaller by becoming very large negative numbers. That is, g of x tends to minus infinity as x approaches 2 from the right. Now, infinity is not a real number as it's not a point in the real number line. Thus, in this case, the side limit does not exist. We write this as the limit of g of x as x approaches 2 from the right is minus infinity or it does not exist, which we abbreviate as DNE. Both answers reflect the fact that the limit is not a real number. Depending on what sources you are using to study, one or both answers are acceptable. Likewise, g of x approaches infinity as x approaches 2 from the left. Hence, the limit of g of x as x approaches 2 from the left is infinity or it does not exist. We conclude that the limit of g of x as x approaches 2 does not exist, since at least one of the side limits doesn't either. Note that in this case we cannot write that the limit of g of x as x approaches 2 is infinity or minus infinity, since the side limits are different. One can do a similar analysis as before, or argue by using symmetry of the question and symmetry of the graph that the same conclusion must also be true for the limit point c is equal to minus 2. Hence, the limit of g of x as x approaches minus 2 does not exist. This example illustrates that although infinity or minus infinity are not real numbers, they can arise as the limiting behavior of a function. Thus, we need to pay special attention when dealing with infinities. This is a recurring theme in calculus and one we will encounter often. In an upcoming video, we discuss limits from a formal perspective throughout the use of the epsilon delta definition and apply it in examples. This was a surfing math lesson. Until the next one.